everyone, welcome to part 1 of chapter 2. Today we are going to talk about the electromagnetic spectrum and light, and we're going to use that to then talk about the line spectra of atoms and then relate that to how the electrons are actually arranged in the atoms and start talking about things like electron configurations. So lots to cover today. Let's get started. So you may have heard this term electromagnetic radiation, and it may sound kind of scary or sciencey or dangerous, right? But electromagnetic radiation is not dangerous. We experience electromagnetic radiation literally every day. You'll experience it when you listen to a radio or use the microwave, or if you see a rainbow outside, right? Or if you go to the dentist or the doctor and you have an x-ray taken. All of these are electromagnetic radiation. And all types of electromagnetic radiation, including light, consist of particles that move as waves of energy. So they're little particles, like little pieces, that actually move as waves, which is kind of cool. So we're going to get into that today. But I want to be clear, electromagnetic radiation is not some scary, dangerous thing. We experience it all the time. Okay, so what is it? What's our definition? Electromagnetic radiation is a form of energy that runs a continuum all the way from radio waves, which are really, really long, to X-rays, which are pretty smaller. That's also got visible light in there, and microwaves, which is not the contraption that you use to heat up your food, but those waves that are being emitted from that microwave. But lots of different forms of energy. Each form of radiation shares some common characteristics because they are all energy, right? They have things in common. They display wave-like properties and they all travel at the same speed. So this speed is actually the speed of light. So even your radio or your microwave, all of those radiation, right? All of that is traveling at the speed of light, which is pretty cool. We're not going to get into the math related to electromagnetic radiation in this class, but you will experience it if you go on in chemistry or if you take some physics courses. So let's talk about wavelength. So the way that we talk about these different types of radiation is we're looking at the differences in their wavelength. Okay, these waves that we're thinking about with energy are pretty similar actually to waves that you see on the beach. Right? If you think about the waves on the beach, like this, right? They have different crests, and maybe if you're surfing, right, you're trying to look for the crest of a wave and things like that. They're kind of similar to that. The highest part at the very top is called a crest. So like if this was our wave, this would be the crest up here at the top. And the bottom part, the lowest point, is called the trough. Okay. So same thing here. If we're looking at these, right? This is the crest. This is the trough, and all waves have these. But like I said, we're going to use the wavelength to talk about the differences in our waves. So the wavelength is always the distance between consecutive crests. So you're going to find two crests that are next to each other, like these two, and you're going to measure the distance between them, and that distance is the wavelength. In this class, like I said, we're not going to associate numbers with these. We're just going to talk about whether something has a longer wavelength or a shorter wavelength, because we're not going to do any calculations with this. So the wavelength on the top, right, wavelength A, this has a much longer wavelength than wavelength B. And so that means that these waves will behave differently because they have different wavelengths. The other thing that we use to describe waves is frequency. Frequency is technically defined as the number of times a wave passes through a certain point per second. Okay, since we're kind of looking at these waves in a static fashion, let's say that this is kind of our time frame that we're looking at. Okay, this is one little snippet in time. If you look at wavelength A, there's not so many waves in that time, right? Because it has a really long wavelength, it doesn't have a lot of waves that happen in this point in time that we're looking with, which means that it has a low frequency. So if you look down at wavelength B instead, right, because wave B has a much shorter wavelength, it has a much higher frequency. Do you see there's a ton of waves that happen in this time period for wavelength B just because that wavelength is shorter. So we call this an inverse relationship. If it has a short wavelength, like B, right? B has a short wavelength and a high frequency because there's a lot of waves that are happening in this little snippet of time. Whereas wavelength A, or wave A, has a longer wavelength, right? Much longer, greater distance between these waves. Therefore, it has a lower frequency. There's fewer waves that happen in our little snippet in time. All right, so I was talking earlier about the electromagnetic spectrum or electromagnetic radiation, right? And so we put all of these different types of radiation on a spectrum, and so we can talk about where things are with respect to each other. So things that are over here on this side, right, on our left, are going to have a really, really long wavelength, okay? These have long wavelengths, whereas the stuff over here has very short wavelengths. And you can see that, right? If you look at this little picture, those wavelengths are very, very close together, whereas these are very far apart. Okay, and so it's just been arranged in order of the size of the wave, right? The electromagnetic spectrum is an arrangement of the different types of radiation from the longest to the shortest wavelength. Okay, so starting over here on the left, right, we have power lines, really, really, really long wavelengths. And then slightly shorter, we have AM/FM radios. Okay, so if you'll notice, when you're driving kind of out in the middle of nowhere, let's say we're like driving through Arizona, right? You may not get cell reception, but you likely get AM or FM radio, right? So you're not totally bored in the car. The reason for this is that these waves are really, really long, and they actually have the ability to kind of jump over mountains or around mountains because these wavelengths are almost a mile long. Think about that for a second. The distance between the crests of these waves is about a mile. That's nuts, right? But it's able to reach around mountains and get to places where cell reception may not happen because of that long wavelength. And then moving on, like I said, your telephone uses electromagnetic radiation. Your cell phones, right? See here, cell phones, much shorter wavelength than your radio, which is why that cell reception doesn't happen in some places where AM or FM radio does. And then we hit, keep going that way, we get to microwaves. So microwaves use electromagnetic radiation, and a common thing that I hear people talk about is they'll say, oh, my mom told me don't stand too close to the microwave because it has radiation, or don't look at your food in the microwave, right, because you're going to get hit with the radiation. And while that's true, the radiation from the microwave cannot hurt you. Okay, I want you to make a note of this. The radiation from the microwave can't hurt you. Do you see right here? This is where visible light is. Okay, so anything this way of the visible light, this stuff is not dangerous. Okay, it can't hurt you. So there was a while back, people said don't sleep with your cell phones under your pillow because, the radiation, all of that. Because the cell phone and the microwave have such long wavelengths, they actually can't hurt you. It's not going to damage your cells, okay? So sleeping with your cell phone under your pillow might be weird, or looking at your food in the microwave, is kind of waste of your time probably, but it's not going to hurt you. Anything this way from the visible light, this is dangerous, okay? This stuff has the ability to actually go in and damage your cells. And by damaging your cells, it can cause things like cancer and other problems. But because the stuff over here has such a long wavelength, it can't damage your cells and therefore can't give you cancer or any other problems. So cell phones, TV, microwaves, totally safe. Stand as close to them as you want, okay? Let's see, we've also got over here, we have heat lamps. Again, also not dangerous because they're to the left of that electromagnetic radiation, of the visible light. But heat lamps are things like if you play some online video games and you wear those infrared goggles in the game, you can sometimes see that infrared radiation, right? That heat coming off of people. That's where you know where people are. That is what is being given off of your body all the time. You are giving off electromagnetic radiation, right? You are giving off heat, which is cool. So do, incandescent bulbs, like in your ceiling fans or in lamps at your desk, all of that. So heat also is energy. And then we get to visible light, okay? Visible light, I want you to think of Roy G. Biv. And so if you didn't learn this in elementary school, I want you to remember it now. These are the colors of the rainbow. So it stands for red, orange, yellow, green, blue, indigo, violet. Okay, and it's important to remember them in this order because it will help you to know which colors have more energy than others. On this side, this is the low energy side. Okay, low energy and also long wavelength. That's the abbreviation for wavelength there. That's the Greek letter lambda. Okay, so red has the longest wavelength and also is the lowest energy. Okay, whereas if we look over here at violet, violet is going to have the shortest wavelength. Oops, sorry, there you go. Shortest wavelength, and it's very high energy. Okay, so I want you to know the order of this rainbow: red, orange, yellow, green, blue, indigo, violet, or Roy G. Biv. Okay, again, red is the longest wavelength, lowest energy, and then violet is the shortest wavelength with the highest energy. Okay, if we keep moving on past visible light, we'll get to ultraviolet radiation. Okay, you're likely familiar with UV rays because we live in California, right? If you go out in the sun, you are going to be exposed to UV rays. So if you are fair-skinned, or even if you're not, it's really important to put on sunscreen to protect yourself from this ultraviolet radiation. Remember, I was talking about earlier that anything that's this way, right, anything to the right of that visible light, that's where it starts to have a small enough wavelength that it can damage your cells. So the fact that ultraviolet radiation is to the right, that means it is in fact harmful. That's why people get things like skin cancer. The UV radiation can go in and interact with your cells and damage them. And when it damages your cells, your body sees that damaged cell and it says, like, go get it, kill it, it's wrong, right? And that can lead to things like cancer and other problems. So ultraviolet radiation, dangerous, put on sunscreen. And then we get to things like medical x-rays. So x-rays, you shouldn't get x-rays when you don't need them, right? X-rays are important. They can help you see if you've broken a bone or, look at your dental health. But you don't want to get too many x-rays because, again, they're to the right of this visible light. So those x-rays can damage your cells, right? That's why when you go and let's say you go to the dentist and you're going to get an x-ray, they put that lead vest on you to protect your vital organs from the x-rays, right? It's so that those x-rays that they're using to look at your teeth don't go and damage your cells, okay? It's fine, and I want to be super clear, it's fine if you just get x-rays every now and again. You're going to be perfectly safe. You just don't want to go in and get them every single day. That's why the dental hygienist, when she takes those x-rays of your teeth, right, she leaves because, she can't be exposed to x-rays every single day. Otherwise, she'd be in danger of getting things like cancer. And then we have gamma rays, which are all the way to the right. They're our shortest wavelength, and those are actually used to treat cancer. Kind of ironic, right? I told you everything to the right was dangerous. It is. Gamma rays have wavelengths that are short enough that it can go in and actually kill cancer cells. So if you hear that people are going through chemo and radiation, it's the radiation component. That's gamma rays. We can use targeted gamma rays to kill those cancerous cells, which is really neat. So moral of the story, everything to the right of the visible light, dangerous, could be harmful. Everything to the left of the visible light, not dangerous, totally fine. So like I said, cell phones, microwaves, all that good stuff, you're totally fine. So the stuff over here, right, let's say on this side, these have very long wavelengths, which means they have a low frequency and they are low in energy, which is again why I told you that red has the longest wavelength and the lowest energy because it's on the left-hand side of this visible light. Whereas, the violet is on the right-hand side of the purple light, so it's going to have things like very short wavelengths. It's going to have high energy. And it's going to be very high frequency, okay? So this is kind of your summary. If you have a high frequency or a shorter wavelength, so that would be the right-hand side, those are associated with larger energies. So gamma radiation is extremely high energy because it has very high frequency and short wavelength, whereas power lines have very long wavelengths, which means they are low in energy and low in frequency. All right. we've talked a lot about electromagnetic radiation. I want you to go ahead and pause here and work on the problems number 1 through 4 on the Chapter 2 lecture worksheet. You can use this little electromagnetic spectrum here to help you out. Once you're done, unpause and come back and we'll keep going. Alrighty. So we were talking about the electromagnetic spectrum, which is talking all about different types of radiation. We're going to narrow it down now, and we're going to talk just about the visible light. Remember that portion, that whole Roy G. Biv? We're going to talk about that now. Okay. So let's say that you have some white light. Any light will do. Let's say it's the light in your, ceiling fan. If you take that white light from your light bulb and you pass it through a prism, okay, if you pass it through a prism, then you're going to see a rainbow, which is really cool, right? And that's what we were talking about, that Roy G. Biv. So in this light, you have all of the colors of the rainbow combined. The prism here actually goes and splits all this different light based on their wavelength. So since red has a shorter wavelength than violet, right, they get kind of spread apart when they go through this prism. It's pretty cool. The raindrops actually, or any kind of moisture in the air, does the same thing with the light from the sun, which is why we see a rainbow in the sky. Those raindrops are splitting the light into kind of different bands based on the frequency of light, and so we see a rainbow. Pretty cool. When we heat atoms, so instead of heating a light bulb or turning on a light, now we're going to talk about heating atoms. So when we heat atoms of a specific element, they also produce light, which is cool. So if you were in lab and you stuck, some element in the fire, it would produce light. But it's not going to produce white light like the light in your ceiling fan. It's going to produce colors, but not all of the colors, just specific ones. So like sodium streetlights make a yellow color. Or if you have a neon sign, that makes a red color. So it's not white, but they're giving off very, very specific colors. And these colors are being produced when electricity or energy is exciting those electrons. Okay, and so we're going to talk more about how do we excite electrons and how does that let us know things about the atom, which is cool. So when a light is emitted from heated elements, so not a white light, not a light bulb, but a heated element, and then that is passed through a prism, it does not produce a continuous spectrum. So it does not give a rainbow, okay? Instead, we see a line spectrum, okay? And this is a line spectrum shown down here. It has different colors, and they are separated by dark areas. So instead of getting that whole Roy G. Biv effect, when we heat elements, we are just getting dark spaces and a couple bands of light, which is cool. That's telling us that only certain wavelengths of light are being produced by the heated element. And this actually can act as a fingerprint for elements. So let's say you had some mystery chemical in your lab and you're like, I don't know what this is. One of the ways of identifying it could be to simply light it on fire and see what color is produced, right? You could run that light through a prism and see what bands you're getting. Like this one here, this is the line spectrum of hydrogen, and it's only for hydrogen. This is like a fingerprint. If we had any other element, it would look totally different. The only way we're getting this specific spectrum is for hydrogen. So it's pretty cool. It's not the best way of identifying elements, but it is one way that you can. So here's some other examples. So let's say we had strontium, right? That's the one up here, SR. If we have strontium and we light it on fire, it produces this really pretty brick red color. It's really cool. So it's got a brick red flame. If we take that light and then put it through a prism, it'll split and look like this, okay? And again, that's only for strontium. You can see it looks totally different than the one for hydrogen that we were talking about earlier. If you light barium on fire, that's this one down here, it's going to produce a green flame, which is really cool. If we send that green light through a prism, then it will split as well, and it will give us this spectrum, right? And so you can see the spectrum from barium and strontium, again, totally different. So based on, this line spectra, we can identify what our elements are. Pretty cool. And what's even cooler is that this line spectra turned out to be critical to the development of the models of the atom. Okay. Remember last time we were talking about Rutherford's model. He discovered the nucleus, if you'll recall. He said those protons and neutrons, they're in the middle, they're in the nucleus, and they're surrounded by electrons. Remember, he was doing that gold foil test where he was shooting alpha particles at the gold foil. Most of them went straight through, but some of them bounced off, and he said, hey, there's something hard and positively charged in the middle. That's the nucleus, right? And so he's credited with finding the nucleus. So he changed his model. He said there's a nucleus in the middle, there's electrons going around the outside, and he said that the electrons orbit the nucleus like planets orbit the sun. So his model is sometimes called the planetary model of the atoms because of this statement, which is kind of fun. So it was a good thought, right? We talked last time that every time our model of the atom changed because we learned things, right? It was a good change, but it wasn't quite right. The same thing is also true for Rutherford's model. It incorporated everything known at the time about the model of the atom, but one major problem is that it couldn't explain the chemical properties of these elements. So, not super helpful, right? If it can't explain the chemical properties of the elements, then what's it good for? So, his student actually, Niels Bohr, said, hang on, I've got an idea and I can make this better. Okay, he changed Rutherford's model to include new discoveries about how the energy of an atom changes when it absorbs or emits light. So he took this information from the line spectra that we were talking about earlier and combined it with Rutherford's model of the atom to make a new model of the atom, the Bohr model. Okay, so he said, all right, there's still a nucleus. That was good. Good job, Rutherford. But instead of these electrons just kind of hanging out on the outside, they have very specific places where they can or cannot be in the atom. So they're only found in specific circular paths that he called orbits around the nucleus. So he said, like the electron could be here, or it could be here, right? It could be on one of those two circles, but it can't be in between, and it can't be out here. It can only be on either this middle line or it can be on this next line, right? There are very, very specific places they can be, and that's called orbits. We will also kind of relate these to energy levels, which is the specific energy an electron in an atom can have, right? They can have enough energy to be here, or they can have enough energy to be there. Okay. So let's talk more about the Bohr model of the atom. So again, he said there's going to be a nucleus, right? That's the thing in the middle. And we're not going to talk more about the nucleus right now. We're just going to deal with the electrons. And he said that, remember, the electrons could be here, they could be here, or they could be here, but they can't be in between. So one of the most important things is that electrons will reside in the lowest unoccupied energy level. So if we only have one electron, it's going to be in the lowest energy level possible. The lowest energy level is going to be the one that's closest to the nucleus. So that's why this electron is sitting here instead of on this one or on this one. It's going to be as close to the nucleus as possible. And again, our electrons have to be in a specific orbital. So it can be here, it could have been here or here, but it can't be in between. We give these orbitals numbers, okay? And they're denoted by the letter N. So N equals 1 is the first energy level, N equals 2 is the second, and N equals 3 is the third, and so on and so forth. The lowest numbered energy level is closest to the nucleus, and then it will get larger and larger numbered as we go out. Okay, so again, the closer to the nucleus it is, the lower in energy it is. If this electron was way out here, then it would be higher in energy than it was previously. Okay. So one thing that's really important is that when we were talking about those line spectra, remember all of those lines that were being produced separated by the black spaces? What's happening there is when our electron gets hit with some energy, so this could be like heat or electricity, right? But it needs energy of some kind, okay? When it gets hit with this energy, that electron jumps up to a higher energy level. This is called being promoted. So instead of hanging out in that lowest energy level where it normally is, by absorbing that energy from heat or electricity, it jumps up to a higher energy level. It's promoted. Okay? When that electron is done with its energy and it returns to the ground state, so it comes back here. When it goes back to where it came from, it releases all of that energy as colored light. Okay, and that colored light is what we're seeing on that line spectra. Those are all those different lines. That's when an electron jumped up to a higher energy level, fell back down, and released the energy. Okay. The farther an electron falls, the more energy that's being released. So let's say this electron, let's say there was an electron here, and it fell back to the ground state. That's a long way to fall. Maybe that was going to be, that released some violet light because it's higher in energy. Okay, whereas something that fell a shorter distance, maybe just from this energy level back to here, this maybe produced red light because it's lower in energy. Okay, so the farther an electron falls, the more energy that's released. Okay, and again, this is your little reminder. Color red has the least amount of energy, violet has the most, and we're going to remember this as Roy G. Biv. Okay, so the color of light that we are seeing, whether it's red or orange or yellow, etc., right, that color of light that we're seeing tells us how much energy is being released by the electron. Right? If it's red, then it's releasing very little energy and that electron didn't fall very far. But if it's violet, then it's releasing a lot of energy and that electron fell a great distance. Okay, so we can use these, those colored bands, right, that line spectrum, to start to tell us where the electrons are in the atom, which is really cool. So we can use this light to help us understand more about the atom. Okay, so again, if you have something that's absorbing a little bit of energy, then it's going to jump up a little bit, fall back down a little bit, and it's going to produce some low energy photons. Okay, and you may not be familiar with that term photons. For now, let's just think of it as another term for light. Okay, if it absorbs a lot of energy, then it can jump up a great distance and then fall back down a great distance, and it released high energy light. So again, the more energy that's being absorbed and released, the higher frequency of light or the higher energy of light that's being released. So the way this actually plays out with respect to our models of the atom is that electrons orbit the nucleus at different distances. So if we think about that line spectrum that we saw earlier, and we had like a red band and some yellow and greens and all different things, those ones are each talking about different distances that electrons can be because they're all giving off different colors. Okay, so electrons are orbiting the nucleus at different distances because we are seeing different lines in this spectrum. Okay, so again, when an atom absorbs energy, it's going to promote that electron. When that energy is released, the electron will go back to the ground state or decay back to a lower energy level. All right. So again, ground state is going to be the lowest energy level for the atom. So that's what I was talking about when it comes back down. It's going back to the ground state, back to where that electron came from. And each line in that spectrum corresponds to the emission of energy as an electron relaxes from a higher energy level to a lower energy level. So when that electron goes back to where it came from, it's giving off some colored light. And the color of light depends on that gap, right? The distance that it falls. And so the cool thing is Bohr's theory about, okay, there's a nucleus and there, the electrons can be here or here, but it can't be any in between. Bohr's theory worked really, really, really well to explain hydrogen, but it didn't explain the line spectra of any other atoms. So again, Rutherford, it didn't explain, his model didn't explain anything about the atom. Now Bohr, his student, got a little bit closer. Right now he could explain the line spectrum for hydrogen, but again, what about all the other elements? So we know our model isn't quite right, because if we had the right model of the atom, then we would be able to explain all of these line spectrum. So again, it's like we're getting closer, but we're not quite there yet. For the level of this class, though, just so you know, we will actually use the Bohr model of the atom. Even though I just told you that it's not quite right, it's actually pretty close. And it's going to be very, very close for what we do at the level of this class. The real model that we'll talk about in a little bit is called the quantum mechanical model, or sometimes called the Schrödinger model. And it requires the use of quantum mechanics, so some quantum physics, Calc 3, and a lot of other stuff. So we're not going to mess with that in this class. The Bohr model of the atom is really good, just not quite right. But again, we're going to use it in this class. So for now, we're going to go ahead and take a break, and we're going to work on problems number 5 through 8 on the Chapter 2 lecture worksheet. So go ahead, pause here, and then come back when you're ready to move on. Alrighty, so like I said, the Bohr model of the atom was good at explaining the line spectrum for hydrogen, but didn't explain the line spectrum of any other atoms, which you could imagine is a pretty big problem because we deal with atoms other than hydrogen. So we need to know what's happening with those electrons. Okay, so in 1924, de Broglie, a French chemist, he proposed that matter could be treated as either a wave or a particle. Remember earlier when we were talking about electromagnetic radiation, I said it was a particle that's traveling as a wave. So that's called the dual particle wave nature of matter, or the wave particle duality of light. Okay, you're going to treat, or we are going to treat matter as either a particle or a wave. So that means, right, remember we were talking about the term matter? Matter is anything that has mass or occupies space. So that includes you. We could treat you as a particle, right, as just a person, but we could also treat you as a wave, which is kind of weird to think about, right? So he said, though, for very large objects, the wave properties are negligible due to a very small wavelength. The way that this plays out is that the larger the particle, and compared to atoms, we are very, very large. So our wave component would be very small, which is why we don't talk about people as waves. But for small objects with less mass, like an electron, okay, the wave-like properties of the matter become really, really important. So the reason that this Bohr model wasn't working is because we were trying to treat the electrons just as particles. But they're not just particles, they have a wave component. And so we have to take that wave component into account in order to correctly model the atom. So in 1926, Schrödinger expanded the wave-like properties of matter, and he developed an equation to describe the electrons as waves. So he took those particles, right, those electrons, and he said, okay, the particles are going to act like waves, and here's a mathematical equation for how they act. Okay, his whole theory is called quantum mechanics, and it allows you to calculate the probability of finding an electron in space. So again, he's finally figured out, right? Schrödinger has figured out how the electrons are behaving in the atom, and we're able to much better model what the electrons are actually doing. The problem with this is, like I said, it requires a lot of quantum physics, Calc 3, all kinds of other madness. And so we're not going to mathematically describe this in this class. And like I said, the Bohr model actually does a really good job of describing the atom. So we're more going to talk about this on a qualitative matter rather than doing any calculations with it. But this wave-particle duality of nature says that, okay, instead of the electron, right, we talked about Bohr, here's the nucleus, and here's where our electrons could be. Well, instead of saying the electron is on this line, quantum mechanics says the electron will be somewhere in here. Do you see all of these dots, right, in this? This is the atom, okay? Here's our nucleus, and you see all of those dots. And you may at first think, wow, that's a lot of electrons. No, it's actually just one electron. This is the model for the hydrogen atom, okay? And so all of those blue dots are showing all of the different places that one electron could be, okay? So you see how this could be kind of a mess to try and talk about the atom with. But quantum mechanics deals in these probabilities. Instead of having orbits like Bohr, right? These were orbits. Here's orbit 1, here's orbit 2, right? Instead of talking about those orbits, now we're replacing them with orbitals. And orbitals are defined as a region of space with a high probability of finding an electron. So here's the orbital for hydrogen, and it says in there you will find probably that one electron somewhere in there. It's gonna be there, probably. Okay, and so that's how we are now describing our atom. And I think in a lot of ways it will seem to you like a step back. It's like, well, no, this seemed pretty good. It was going to be on the line, right? And whereas this seems like a step back. That's true, but this is actually what's really happening. Okay, so Bohr's idea of that whole, like, again, 1, 2, right, and so on, those orbits and those quantized energy levels where it could be here or here, but not in between, it does have some parallels in quantum mechanics or with this quantum mechanical model of the atom. So instead of calling them orbits, we're going to now think of them as principal energy levels. And you see that N again that I was talking about earlier. This N, or this principal energy level, is giving you an idea of the distance that electron is from the nucleus. So if it has N equals 1, then that electron is going to be closer to the nucleus than N equals 2 or N equals 3, right? Remember, those N's, they get larger as the distance from the nucleus increases. So N equals 1 is going to be the closest to the nucleus with the lowest energy electrons. As we get greater and greater numbers, they're getting farther and farther from the nucleus and higher energy. Okay, in this energy level can be any positive number, 1, 2, 3, etc. We'll deal with up to 7 energy levels. Okay, so again though, even though we're not talking about the Bohr model, these electrons can only have certain energy values. So that was right. When he was talking about like an electron could be here or here, but not in between, that's still right. Even though we're talking about them as probabilities now, it's still the right idea. So it can be close to the nucleus or it can be a little bit farther or farther, but at these very specific distances. You can think about them as like this, books on a bookshelf. You can put the books on the first bookshelf or shelf, or you can put them on the second shelf or the third shelf, but you can't put them on like the 2.5 shelf, right? They can't sit there. They'll fall to the second. And so you can think about that, or like standing on a ladder. You can stand on the first rung or the second rung, but you can't stand in between. This is the same thing for the electrons. It can be in that first energy level or in that second energy level, but it can't be in between. Okay, so since it can only be in these specific energy levels, we say that it is quantized. It has a specific amount of energy that it can or can have. Okay, that's what that term means, specific amount of energy. All right, so these orbitals that I was talking about earlier, right? Those areas where an electron could be, they have very specific shapes. And these shapes are identified by letters, and they are S, P, D, F. Okay, so these energy levels are containing sublevels. So again, energy levels, I know this is a lot of terminology. Energy levels are like N equals 1, 2, 3, 4, etc. Those are talking about the distance from the nucleus. But within each one of those energy levels, they have sublevels. Okay, and those have different shapes, and they are denoted by the letters S, P, D, F, or like you'll hear me say SPDF, and I'm going to say it a lot. My apologies. I say weird things. You're going to remember SPDF, because that's going to tell you the order of the orbitals in order of energy, and it's going to be important for this chapter. Okay, so again, an atomic orbital is a region of space around the nucleus where there is a high probability of finding an electron. And by high probability, we mean like there's a 90% chance it's in there. There's still a 10% chance it decided to wander off to somewhere else, but it's probably in there. Okay. Here are the 4 shapes of the orbital. So here is S, P, D, and F. And so we're going to talk about these different shapes as we go through. Okay. So here, though, on the right-hand side, this is a Bohr model of the atom. And again, I told you at the level of this class, we are going to talk about the Bohr model, not about the Schrodinger model or the quantum mechanical model, because the Bohr model for the level of this class and for the level of Chem 1 and Chem 2, it's not just us, is good enough. Okay, so here's our n equals 1, n equals 2, n equals 3. But now you're starting to see the S and those P show up, right? So that's telling you that there are different sub-levels in that energy level. So let's talk about that. So in the n equals 1, so that's the very first energy level, that is the one closest to the nucleus. It only contains one sublevel, okay? And that one sublevel is called the 1s orbital. So the s orbital looks like this. It's a spherical. It essentially looks like a basketball, okay? So the 1s is spherical in nature, as are all s orbitals. So anytime you talk about an s orbital, you're going to think S stands for spherical, okay? S means that it's essentially a ball. If it's a 1s, that means it's close to the nucleus. If it's a 2s, that means it's a bigger ball, farther from the nucleus. 3s will be an even bigger ball, farther from the nucleus, okay? But they're all going to be spherical. They're all essentially going to be shaped like a ball. Okay, so in this s orbital, there's a 90% probability of that electron being in there. And again, for the level of this class, we're going to say it's in there for sure. All right, so let's talk about this orbital. So this orbital here, this 1s orbital, is going to follow the Pauli exclusion principle. And that means that an atomic orbital, such as that 1s, can hold 2 electrons. And these 2 electrons have to have opposite spins. Again, I think that's going to be a little bit weird for this class, right? You're like, what do you mean spin? Essentially, the electrons are both, right? Because there's going to be 2 in this orbital right here. There's going to be 2 electrons in there, and they have to have a different kind of address. So one of them is going to be denoted as spin up, and the other one will be spin down, just so that we have different ways of talking about them. Okay, they're always going to have opposite spins. If one is spin up, the other will be spin down. More on that in the next lecture. Okay, so 2 electrons can fit in this 1s orbital. All right, now let's look at the second energy level, principal quantum number 2. So now we're not on that, if we're thinking about the Bohr model, we're not on this first one anymore. That was only the 1s. Now we're on this second energy level out here. It contains 2 sublevels. It has a 2s. So remember, 2s means it also has one of those spheres, but now it's just bigger. It's farther from the nucleus. And it also has now 2p orbitals. Okay. The 2p orbitals have the 2p sublevels, my apology, have 3 different orbitals. px, py, and pz. And I don't need you to remember those. Okay. All I'm showing you with the px, py, pz is that it has different orientations in space. So we call these, like in chemistry, we call these types of orbitals dumbbells. Okay, so this dumbbell is along the x-axis, this dumbbell is on the y-axis, and this dumbbell is z. That's why they say x, y, and z. And again, we're just doing that to talk about the fact that there are 3 of them and we need to denote them differently. Okay, but essentially what I want you to remember is that there is a 2s. It has one orbital, one 2s, and there can be 2 electrons that go in it. The 2p has 3 orbitals, 1, 2, 3, okay? And since there are 3 orbitals, and we said 2 electrons can go in each one, that means 6 total electrons can go in those 3 orbitals, okay? I know this is a lot of information. I will have a summary slide in just a little bit, I promise, okay? For now, just try and take it all in and take notes as you go. All right, now we're going on to principal quantum level 3. So again, here's the nucleus, here's the first energy level, second, now we're way out here at the third, okay? There are 3 different sublevels. So now we have 3s. Okay, so again, that's going to be a sphere, right? That basketball, but it's going to be even larger than the 2s. It's going to be even farther from the nucleus. Still a sphere, just farther out. It also has the 3p orbitals. So remember, there were 3 of those p dumbbells. and 2 electrons could go in each one, so there's 6 in there. It also now has another new thing. It has 3 d orbitals. So these are the d orbitals down here. We call these double dumbbells and a dumbbell with a donut. It's a lot, right? So if you look, like this one, there's double dumbbells, double dumbbells, double dumbbells. This one has a dumbbell with a donut and more double dumbbells. So that's how I would remember these. I want you to know, I am not going to ask you to draw any of these at any time. Okay. When you're doing your homework, you may have to identify whether something is an S, a P, or a D, or an F, but I'm not going to make you draw them. So please do not spend your time trying to draw double dumbbells and a dumbbell with a donut. Okay. I just want you to be able to recognize what a P orbital looks like versus a D. Okay. So since there are 5, right? 1, 2, 3, 4, 5 different orbitals. And remember, 2 electrons can go in each one. That means you can have 10 total electrons in these 5d orbitals. All right, so that was a lot, right? What I want you to remember is that within this energy level, within whether it's, n equals, 1, 2, 3, etc., the S sublevel is always going to be the lowest in energy. It's always going to be the closest to the nucleus in that particular energy level. And then P, and then D, and then finally F, which we didn't talk about. We won't talk about the F orbitals too much in this class. Just they get a little wonky. So we're mostly going to keep it to S, P, and D. But here is our order. S, P, D, F. The S is the lowest energy, the F is the highest energy. So remember, I told you earlier, I'm going to say the term SPDF a lot. SPDF will help you remember SPDF. Okay, or you can remember SPDF, but that sounds a lot less entertaining. So SPDF, S is the lowest energy, F is the highest in energy. All right, this is our summary slide for today. In the S sublevel, right, there is 1 orbital. Remember, each orbital can hold 2 electrons, so there's 2 electrons total. In the P sublevel, you have 3 orbitals. Remember that Px, Py, Pz. Each one of them can hold 2 electrons, so 3 times 2 gives us 6. In the D, right, there were 5, those double dumbbells and a dumbbell with a donut. So since there were 5 different orbitals and each one can hold 2, there are 10 electrons total. And then we didn't talk about F, but F, there are 7 orbitals. They just look kind of crazy. And then each one can have 2 electrons, so there are a total of 14. So what I want you to remember is SPDF is odd. Okay, me saying SPDF over and over and over is odd, right? Maybe I'm odd, but SPDF is odd. So that's how we're going to remember the orbitals. SPDF is odd, 1, 3, 5, 7. All of the odd numbers in order, okay? So SPDF is odd, 1, 3, 5, 7. So when you're on your, quiz or test, you're like, all right, SPDF is odd, 1, 3, 5, 7. And each one of those orbitals can hold 2 electrons. So you take, this and you multiply it by those 2 electrons to figure out how many electrons can be in each one of those sublevels. Okay, see? I told you I'd find you a summary. All right, so thinking about this whole SPDF is odd, right? Use that to figure out the maximum number of electrons that can go in a 4D sublevel. I'm going to pause here, try it out, and then press play when you're ready to see the answer. All right, so what is the maximum number of electrons that can fit in a 4D sublevel? We actually don't care that it's a 4D, okay? The fact that it's a 4 in the front is only telling us that it's pretty far away from the nucleus, right? Remember, as that number in the front gets bigger and bigger and bigger, that's telling us those d orbitals are farther and farther and farther from the nucleus. But it doesn't change their shape or how many electrons it can hold. So the thing we really care about is that the fact that this is a d sublevel. Nobody cares that it's 4. We care that it's a d sublevel. Since it's a d sublevel, it has 5 orbitals, right? Remember, S, P, D, F, 1, 3, 5, 7. So D has 5 orbitals. Remember, to figure out the number of electrons, we're going to take this and we are going to multiply it by 2 to figure out how many electrons can fit in there, because each orbital can hold 2 electrons. So since we have 2 electrons in each orbital, 10 electrons can exist in this 4D sublevel. Alrighty, I think that was a lot of information today, and that is actually where we are going to stop for this lecture. So before you call it a day, make sure to do problems 9 through 10 on the Chapter 2 lecture worksheet to solidify these concepts we were just talking about in your mind. Make sure to be really solid about this whole SPDF 1357 before you go on to the next lecture, because we are going to use all of that information to start talking about the electron configurations of atoms. So if you have any questions while you're working on this Chapter 2 lecture worksheet, remember, first, check the answer key, see if you're doing it right or wrong. But if you're not, please reach out to me and ask for help. I'm more than happy to answer any questions you have and help you out along the way. So keep working hard, get lots and lots of practice, and otherwise, I will talk to you guys next time.